Okay. All right. So hopefully everybody here got my email from yesterday. So the test obviously now will be on Wednesday. And today I'm covering quite a bit of chapter 6, which is on probability. So this is actually a good time to do that. So I'll cover that.
Professor,
I'm sorry, go ahead.
just want to say sorry for your loss and your family.
Thank you. I appreciate that, Daniel. Thank you. All right. So what we're going to do is I'll share the screen with you and we'll start looking at chapter 6. I've also, of course, extended the homework, as you know, to tonight at 11:59, so you should be okay with that. I'm assuming that you'll be okay with that. All right, so let me find the right one here. This is, let's see, 1, 2, 3,
So,
4.
Professor, just to clarify, we're doing things for chat like the next unit. You said
Yes,
chapter 6. Okay, cool.
yes. So that's exactly right. So we're going to be working on the next unit. Yes. So I'm actually, let me see if I have the right one here. Just give me a second here. Let me see if nope, that's the wrong one. So let me stop sharing that. Let's try another one. That's not it either. Thought I was able to see the 4 that I opened up, but this must be it here. There we go. All right. All right, so I'm going to actually cover the first 4 sections of probability today. What I highly recommend for you, all of you, is to read this chapter and go through the sample probability questions in them. Unfortunately, because this is a 3-credit course, not a 4-credit course, I don't have enough time to cover every type of possible problem, but I can cover quite a bit of it. But for you to get a complete idea of what you need to know, reading the chapter and going over the sample probability questions in this chapter will make it easier for you, much easier. So don't rely on the PowerPoints by themselves. It's not enough. You definitely need to go through the examples in the book and have your calculator with you, and then piece of paper, pen, pencil, whatever, and really go through all the examples in the book. I know it's a lot of work, but it's my experience that people who put that type of effort in do very well, not only in the second test, but for the rest of the course, because probability is an important topic in statistics. So the textbook does a reasonably good job in describing it, and even though you go through it and it may appear, not the easiest thing to learn, especially if you haven't learned it before, you have to believe me that this is a very very elementary introduction to probability. All right, you may not believe it, but it is true, because you can take a probability course that's an entire semester long, that has a lot more detail and requires calculus. What this requires is just very simple arithmetic. It's just arithmetic more than anything else. There's very little in terms of algebra or anything like that. Just a little basic algebra for understanding some of the formulas. Now, probability is one of my favorite topics to teach in statistics. And I think for a lot of professors who teach statistics, it's probably a fun topic. Again, you may not feel that way, but people who like math tend to like probability. Now, you have to get used to, I was telling you at another time that statistics has its own language. And let me just check something here. Somebody's in the chat. Let me just check the chat just quickly. I can't see it. All right, I'll get back to the chat a little bit. So statistics has its own language, so does probability. So probability has sort of a language within the general language of statistics. So, but there's not a whole lot here. There's some definitions, and hopefully they're not going to be over complicated. Now, you all know what an experiment is. We covered that in the last chapter a little bit. Here they're talking about what's called a chance experiment, which is basically, it says here, the process of making an observation when there's uncertainty about which of two or more possible outcomes will result. So a chance experiment could be flipping a coin 100 times, or rolling a die 2 or 3 times, or randomly selecting cards from a card deck. These are what they refer to as chance experiments, okay? We don't know ahead of time which outcome we're going to get, but this is something that we could try to do on our own. We can do this, okay? Here's an example. Consider a chance experiment to investigate whether men or women are more likely to choose a hybrid car over a traditional internal combustion engine car when purchasing a Honda Civic, all right? So the Honda Civic is available with either a hybrid or traditional engine. In this chance experiment, a customer will be selected at random from those who purchased a Honda Civic. The type of vehicle purchased will be determined and the customer's gender will be recorded. So a person is being selected at random. We don't know ahead of time whether that particular customer that's going to be selected has purchased a hybrid or traditional engine Honda Civic. All right, that's the whole idea. So there's 2 possible outcomes: Honda, the hybrid, or the traditional Civic. All right, and if you select somebody at random, it's going to be one of those 2 choices, but we just don't know the result ahead of time. Now, if we listed all the possible outcomes of a chance experiment, that is called a sample space. All right. So this is a term that mathematicians came up with this term. All right. So just know why it seems kind of unusual. But sample space really means all the possible outcomes of a chance experiment. For example, if you flip a coin once, the possible outcomes are heads or tails. All right. If you flip a coin twice, there's 4 possible outcomes. Either they're both heads, they're both tails, the first one's heads and second one tails, or the 4th possibility is the first one's tails, second one's heads. Right? So you could list all the possible outcomes of a chance experiment. Now that's important to be able to count all these outcomes, because that's going to be the denominator of your probability formula, or number that you're going to come up with. It's going to be your denominator, or the counting of all the possible outcomes of a chance experiment. All right. And here's another thing here, where if you choose somebody at random, all right, there's 2 possibilities for gender. All right, and in this case, we'll just assume 2. And then there's 2 possibilities for the type of Honda Civic, hybrid or traditional. So there are 4 possible outcomes. You could have figured it out also, because gender has 2 outcomes. The type of engine has 2 outcomes. You just multiply them, you get 2 times 2 is 4. That's another way of figuring it out. You could also list a sample space in this type of format, where you could have, let's say, if there's 2 variables that you're looking at, gender and the type of engine, then you can list the outcomes using, in this case, parentheses with a comma in between to show all the possible combinations, and then you have brackets around the sample space like that. Okay, so that's one way of listing that. You can also do what's called a tree diagram, where one of the variables is you're given the choice. It branches out for male and female here, and then along one of the tracks, whether it's the male or female track, you have 2 possible outcomes for the type of engine, hybrid or traditional. So you can see the 4 outcomes at the end of the tree here. It's male hybrid, male traditional, female hybrid, female traditional. So a lot of people like this, people more visual, like this sort of way of listing the outcomes. All right, so it's really up to you. I'm not going to ask you to do a tree diagram in any test question, but just know it's a technique for those of you who like it. All right, that's something you can do, or you could just simply list the outcomes too. All right, and it just shows you how to use the tree diagram, which I just showed you. Events, this is another term in probability. Event is any collection of outcomes from the sample space of a chance experiment. So event could be a subset of all the possible outcomes. For example, flip a coin once, an event would be heads, another event would be tails. It is also an event of that the entire sample space could be an event also. All right. A simple event is just one of those outcomes. All right, that's just a definition. Now they use capital letters to represent events. Sometimes A, B, C. Sometimes they'll use the same letter and use subscript 1, 2, 3 like that. All right, so just know that that represents an event. Okay, an example again, gender, male or female, hybrid and traditional for the type of engine. Here's your sample space. So this is another way of listing it, right? Where the first position is male or female, the second position is going to be the type of engine. So MH represents male hybrid car, FH the female hybrid, MT male traditional, FT female traditional. All right, so here are the 4 ways of listing a sample space, right? So hopefully that makes sense. And here are the events. For example, if we wanted to know the event where hybrid was purchased, you have 2 possibilities: a male purchased the hybrid or a female purchased the hybrid. The other event, another possible event is that the purchaser is male. There's 2 possible outcomes for that event, MH or MT, right? Hybrid male, traditional male. All right. I think it makes, hopefully this all makes sense to all of you. This is the type of notation we're looking at, would have been covered in high school mathematics with sets. All right, so those of you might remember that. Forming new events. Sometimes you can form new events through either combining or finding something other than that event. So for example, let's say we have 2 events called A and B. Okay. And let's say for event A, if we wanted to find all of the outcomes that were not in event A, that were in the sample space, we could use this sort of form, A with a superscript with a C, or one of these, but I'm going to use AC, all right? And what does C represent? C is the letter representing the word complement. Notice complement is spelled with a P-L-E instead of P-L-I. When you say something is a complement to something else, you say it helps to complete it. Notice the word complete is sort of in the word complement. So a complement of event A would be something that is in the sample space that's not in A. Because if you put the outcomes of event A and add in the outcomes that are not in A, what do you get? You get the entire sample space, right? A, you can picture this, right? All the outcomes that are in A, then you have all the rest of the outcomes in the sample space, which is not A. You add them all together, you get all the outcomes in the sample space. All right, so we're going to use this A with a superscript C to represent all the outcomes that are not in A. Okay. Okay. We also have 2 other ways of combining events. One way here is called A or B. Now, in the language of sets, again, we're using set notation. We have this like a U type object here. Means A union B. A union B. It means A or B. What does A or B mean? It means that what we're doing is we're combining all of the elements in A with all of the elements of B, and then eliminating any duplicates. All right. So A or B means it's either in A, the element's either in A, or it's in B, or it's in both. All right. So that's A or B. We also have, so that's called the union of two events. A and B is called the intersection of two events. Notice it's an upside down U. Looks like a horseshoe almost. And we say it A and B. Right? A and B. So we're looking at outcomes that are in A, we're looking at outcomes that are in B, and we want to know which outcomes are in both A and B. All right. Now you might say, well, what if there's no outcomes that A and B share? Well, then A intersect B would be what's called the null set. All right, the null set meaning it's an empty set. So you'd have brackets and nothing inside inside the brackets. That's the null set. All right, so an empty set, null set means there's no, in this case, A intersect B would be there's no elements that are in common. Otherwise, you would list the elements that are, when I say elements, the outcomes that are in common between events A and B. All right, so A or B, look for the word or represents union, and represents intersect. All right, so just when you see any word problems, you'll be able to recognize them in that way. All right, now here it says this is just an example. A traffic engineer has been asked to consider whether a stop sign at the bottom of a freeway off ramp should be replaced by a traffic light. Suppose she were to record the turning direction, left or right, of 3 successive vehicles. Well, there's 2 possibilities. They're going to turn left or right for the 3 successive vehicles. And these are the possible combinations. This is a list of all the possible outcomes of those 3 consecutive cars, where L means turning left, R means turning right. So LLL means that car 1, car 2, and car 3 all turn left. RLL means the first car turns right and the second and third car turns left, like that. And there's 8 of them, 8 possible outcomes. Now, how do we know there's 8 outcomes? Because there's 2 outcomes for the first car, there's 2 outcomes for the second car, and there's 2 outcomes for the third car, left or right. 2 times 2 times 2 is 8. And that's how they came up with the 8. All right, and then you could have a subset of these outcomes. These would be events. For example, event A would be the event that exactly one of the cars turns right. Well, that would be either RLL, LRL, or LLR. Makes sense, right? Just one of the 3 cars has an R, or turning right. Event that most of the cars turn right. Okay, excuse me, at most one of the cars turns right. What does that mean, at most? It means either none of the cars turn right, or they only turn right once, one of those 2. So LLL, none of the cars turn right, and then you have the cases where they only turn right once. Or excuse me, one of the cars only turns right. And then C is the event that all the cars turn in the same direction. It's either they all turn left or they all turn right. These are all subsets of that sample space, the 8 outcome sample space. All right, you can find all of these as a list of sample space. So that's important to be able to come up with subsets or events that are within the sample space. You could also have not C. All right, now what was C before? The event that all cars turn in the same direction. Well, not C would be all the other possible 6 possibilities, right? The event that not all cars turn in the same direction, well, that would be the other 6. So C with a superscript C, the superscript C means complement. So events, this is basically saying not C. This is the new event we're considering, not C. And if C is the event that all cars turn in the same direction, not C means they're not turning in the same direction. Also, okay, all right. I see some messages here, that's fine. People are saying. A or C, we can write it A or C, or A union C is the event that exactly one of the cars turns right, or all the cars turn in the same direction. All right. So that would be this case here. This is all the cars turn in the same direction, these last 2, and then exactly one of the cars turns right would be one of these three also. So these five,
Professor,
yes.
what did you say the upside down U stood for? If the
Intersect.
intersect, okay.
That means that means finding the outcomes that are in common, that are in both. Okay. Okay. All right, here's B and C. This is the upside down one you're referring to. Event that at most one car turns right, and so that's one of the ones, that's B, and all the cars turn in the same direction. Event that at most one car turns right. At most one car turns right. That means there's one of those possibilities is what? None of the cars turn right. That's LLL. And the other one event is that all the cars turn in the same direction. Well, the only one that is in common with that one is LLL. All right. Does that sort of make sense? Let's go back to B and C. Find B and C again. Notice if you look at the list of B and look at the list of C, the only one that's in common is LLL. All the others are different. See it? So LLL, all the cars turning left is B intersect C. Okay? All right. Now, there's some terminology that you need to know for probability. And one of them is called mutually exclusive. Another name for this sometimes people use is disjoint, but I like mutually exclusive better. It's more descriptive. You know, I think you'll remember it better instead of disjoint. But what it means is that if you have two events, all right, if they're mutually exclusive, that means they have no elements in common. They have no outcomes in common. Okay. Now, what does that also mean? That means if the two events are A and B, that means A intersect B is null, right? There's no elements in common. It would be an empty set. That's an important concept when we get to what's called the addition principle of probability, when we talk about mutually exclusive, all right? Let's look at an example, see if we see examples. Now, sometimes when we talk about this idea of mutually exclusive events, it's good to draw what's called a Venn diagram. Maybe you're familiar with it. It's basically a rectangle with sets inside. Now, the rectangle would represent the sample space, the whole rectangle. And inside the rectangle would be different sets that are within the sample space. For example, in this first one here, what's colored in here is not A. All right, A with a C is a superscript, the complement of A. Another way of saying this, the complement of A. A is the circle inside. That's an event within the sample space. Anything that's not in A, not in the circle, is colored, and that is the complement of A. A or B means that's A union B, means all the elements that are in A and in B, if you put them all together and then get rid of the duplicates, you would get A and B. So basically, if the two circles intersect, notice there's a common area in between, the whole area here is A or B. All the outcomes are inside this here would be A or B. A and B would be what's in common. It would be where the two events intersect. Makes sense, right? Intersect. That's why they call it intersect, by the way. It's from this Venn diagram way of looking at it. So A and B, or A intersect B, would be the green in the middle here. And mutually exclusive would be where the two events don't intersect at all. There's no elements in common. There's this picture, the two the two events not intersecting at all, being completely separate. Okay. Sometimes if you have three sets within the sample space, or three events, A, B, and C, then this would be A or B or C. It would be all the outcomes that are inside this. Again, getting rid of any duplicates. A and B and C would be where all three sets share the same space. It would be in the middle. And you could have A, B, and C being mutually exclusive, all three circles being separate. Now, obviously, you could get a little fancy with this. You could have where B is mutually exclusive with A and C, but A and C are not. So you could picture A and C intersecting, but B being separate from both. So you can get fancy when you have three events. All right, but don't worry about that. I'm not going to get too fancy with you in all this. And suppose we have K events, K meaning some whole number. So let's say you could have 10. K could be 10 events. K could be 100 events, whatever. If the outcomes are all, let's see what it says here. The events are A through K, A1, A2, or all the way up to AK. If we say they are mutually exclusive, all right, then you could picture all these events being having no outcomes in common. Now, let's see what it says here. K events are mutually exclusive if no two of them have any common outcomes. So if we had 10 of these in one of these Venn diagrams, if they were all mutually exclusive, all the circles would be separate for each of the 10 events. They wouldn't be intersecting at all. But again, we're not going to get too complicated with this, all right? Now, here is an example. Well, let me see if this is a good example. No, I don't think this is a good example, so I'm going to skip this example. It might be a little confusing to you. So let's go on to section 2. All right, again, I'll give you examples that I like for the types of probability types questions, or the type of questions I can ask for this first section. So we'll just skip that last 3 slides there. You could look at it yourself, but again, some of you might be confused by that particular example. All right, so let's see. Definition of probability, I believe, is next. Let's see if it's right. Yeah, definition of probability. Now, what we talked about in section 1 was just some of the preliminary ideas that we will deal with probability, the idea of a chance experiment, sample space, events, but we haven't really calculated probability yet. So that's what we're going to talk about now. Okay. We have 3 approaches for probability: classical, and there's the relative frequency approach, and then there's the personal probability approach. We're going to deal with the classical approach first because for the past maybe 400 or 500 years, there has been arithmetic and math that talks about this classical approach. Believe it or not, many of the first probability mathematicians were religious people, people who lived in churches, monks and nuns and people like that. And it may sound strange, but they would be hired by professional gamblers who were going to different events, and they wanted to know the math behind the game that they were playing. So the religious people came up with formulas, and the gamblers used those to bet on in different games. So that's where probability started. It's obviously more sophisticated now than it was back then, but of course, it's still being used for games, right? Football games and Super Bowl and all that sort of thing. Now, the classical approach of probability for equally likely outcomes, all right? What does that mean? Well, if we have a fair coin and we flip it, there are 2 possible outcomes that are equally likely to occur, heads or tails. If I roll a die, a 6-sided die, a hexagon die, There are 6 possible outcomes, and they're all equally likely. 1 dot, 2 dots, 3 dots, all the way up to 6 dots. So we're talking about that type of approach, probability, games like that. When the outcomes in the sample space of a chance experiment are equally likely, it says here that the probability of an event E, we use this notation here. We use P for probability, and in parentheses, we put in our event letter. In this case, we're using E for event, but we could use any letter, A, B, C, or whatever letter we want. And it's the ratio of the number of outcomes favorable to event E occurring divided by the total number of outcomes in the sample space. Remember, I had mentioned that to you earlier, that counting the number of outcomes in the sample space is important in calculating probability. And here you can see it's the denominator of this ratio. The numerator is the number of outcomes in for that particular event. All right, so probability deals with counting. Counting. It sounds pretty elementary, but it really is pretty elementary. So suppose you have 4 students submitted correct solutions to a math test contest that had 2 prizes, right? The contest rules specify that if more than 2 correct responses are submitted, the winners will be selected at random from those submitting correct responses. We can use this notation to denote the outcome that Adam and Bettina are the 2 selected. So we have 4 students, Adam, Bettina, Carlos, and Deborah. And we're saying that Adam and Bettina are the 2 selected for the prizes. The other possible outcomes can be denoted in a similar way. All right. So here are the how many 6 possible outcomes, right? The samples, the 2 winners. Notice that we're saying that if one of the winners is A and the other winner is B, it's the same thing as saying B comma A. All right. It does the order in which we put A and B here doesn't matter. A comma B says that A what's the name again? Adam and Bettina are the winners. And then A comma C is Adam and Carlos are the winners, like that. So there's 6 possible pairs of winners. And the probability of any one of these being the true winner, the one that's chosen at random from the 6, is 1 divided by 6. Okay? 1 divided by 6, because there's these outcomes are equally likely. And there's 6 of them. All right, suppose we pick another event that says they have the same sex. Well, you go back, you know that Adam and Carlos are males and Bettina and Deborah are females. So those would be, the 2 out of those 6 outcomes would be event E. We want to know what's the probability that the winners are of the same sex. Well, there's 2 possible outcomes for being in the same sex. And so Adam and Carlos, or Bettina and Deborah, I guess it's Deborah, is that the other? Yep, Deborah. There's 2 of those. And then how many outcomes in the sample space? There are 6. So 2 divided by 6, or 1/3, or 0.333. So that's how you calculate a probability in this case. It's the number of outcomes in the numerator for the event, and the total number of outcomes in the sample space in the denominator. We have another one here. If F denotes the event that at least one of the selected winners is female. Okay. All right, and then F consists of all outcomes except for what? All right. Well, there's only one outcome that has all males, right? So for at least one of them to be female would be the other 5 events, right? Let's go back. Look at all the 6 here, right? And the only one that's all male, I think that's what they're saying, all male, yeah, is AC. All the others have at least 1 female. So 5 out of the 6 is the answer for that probability. That's the probability of event F. At least one of them is female. The answer is 5/6. Okay. Any questions about that? And of course, you can get much more complicated. We can look at poker, how many 5-card hands are there? And the formulas for counting get a little complicated, but we're not dealing with those in this course. All right, so this second approach is called the relative frequency approach. You probably are familiar with the term relative frequency, right? When we were doing histograms, for example, and for each of the classes, we would count the number of values in the data set, and that would be the frequency for each of the classes. And then to find the relative frequency, we would divide that frequency for one of the classes by the total number of observations in the data set. So that would be our relative frequency. And something similar happens in probability. Okay. Now, what they're talking about here is the idea that if you flip a coin several times, even though we know if it's a fair coin, the probability should be 1/2 for any toss of the coin for getting heads or tails, we don't know ahead of time if we toss a coin 10 times, how many heads we would get, right? We could get anything from 0 to 10. I mean, it's possible, even though it's highly unlikely, it's possible that all 10 flips of the coin or tosses of the coin could be all tails. It's possible. So there are possible, other possible proportions, we can call them proportions, of the number of tosses that are heads versus tails that are not equal to 50% if we flip the coin several times. Now, what happens, I'm going to show you this diagram here. Along the x-axis here is the number of times we've tossed a fair coin. And along the y-axis here is the relative frequency of heads. So what's relative frequency? It's just the proportion or percentage of heads out of the tosses that we did. So you could see that it sort of moves around. We could have 70, 80%. If we only flip the coin maybe 10 times, it's possible we could have 60, 70% of the tosses to be heads. And you can see it just moves around. But what happens is, as you increase the number of tosses, notice that this diagram here moves towards the 0.5. So if we went to 100 tosses, we went to 1,000 tosses, 10,000 tosses, we would see that the relative frequency or percentage of the tosses that would be heads would be close to the 50%. And this is an important principle about this relative frequency approach. What it says is, if we repeat the process, repeat the chance experiment many, many times, then the relative frequency will be get very close to the classical probability. Right? So, what's a classic probability of getting heads? 0.5, 1/2, right? If you flip a fair coin. If you flip a coin 1,000 times, we would expect that the relative frequency would be pretty close, getting pretty close to that 0.5, to that 1/2. But however, this is a different approach. This is called the relative frequency approach, because what we're doing is we're running the experiment many, many times, and we're seeing what actually results. Okay. But here you go. Here's the same diagram with going up to 1,000 tosses, and you can see that all of these dots represent the relative frequency of heads, and you can see it's all hugging around that 0.5. So it's pretty volatile when the number of tosses is small, but it gets to be very close to the classical answer of 0.5. So this leads to a very important principle in probability, the law of large numbers, which basically says, as the number of repetitions of a chance experiment increases, the chance that the relative frequency of occurrence for an event will differ from the true probability of the event by more than a small number approaches 0. Another way of saying this is kind of more mathematical definition, but really what it's saying is that the number of repetitions of the chance experiment increases, the relative frequency will approach the classical probability. That's really what it's saying. Now, what is the probability using the relative frequency approach? Now it's still a ratio, but the denominator is something else. It's not the number of outcomes of a chance of a particular chance experiment. It's a number of times that the experiment is performed. Right? So if we flip the coin 1,000 times, the denominator would be 1,000. The numerator is the number of times that the event E occurs. So if event E is the getting heads when we flip a coin. So if we flip a coin 1,000 times and we get 520 heads out of those 1,000 tosses of the coin, then 520 would be the numerator and 1,000 would be the denominator. All right, that's called relative frequency approach. We're just repeating the process over and over again. So why do people use a relative frequency approach many times? Many times they don't know. There's no classical probability for some type of event to occur. All right, there's no probability for it. So that would be one reason to use the relative frequency approach. The other approach is called subjective. This, I think, with what most people use. They don't use any math when they come up with their idea of a chance of or a probability of something happening. They just guess at it based on experience, maybe. But just know that probability in general goes from 0 to 1. 0 meaning impossible. You believe it's impossible for something to occur. And the probability of 1 means absolutely certain to occur. So most things in life are in between 0 and 1. Okay? There's some probability that's close to 0, but not 0. And there's other probabilities that are closer to 1. And if it's closer to 0, it means it's not as certain to occur. And if it's closer to 1, it means it's more certain to occur. All right. Now, here is something that you have to know. Probability can never be less than 0. It can never be greater than 1. So if you do a calculation for probability and you get a number that's negative, or you get a number that's bigger than 1, you know you've made an error, because it can never be. How can, first of all, less than 0, what does that mean? That means something is less than impossible to occur? That makes no sense, right? And something bigger than 1 means more than certain for it to occur? That makes no sense either. So it has to be between 0 and 1. It has to be either expressed as a decimal or a fraction between 0 and 1. All right. Now, there are three types of probabilities again. Classical approach, where we are modeling chance experiments with equally likely outcomes. In other words, we know ahead of time what these probabilities are. That's why, I'm giving again the gambling examples, but they're the easiest ones to know. If you have a 52-card deck and you want to know what's the probability of getting a full house, maybe you're familiar with poker, maybe you're not, you can calculate that ahead of time. You'll know that ahead of time. Right? And that's why a full house, for example, beats 3 of a kind, because why? Because the probability of it occurring is smaller. Makes sense, right? If something is smaller, has a smaller probability, it means it's more rare, and therefore it wins over another type of hand, which is not as which is more frequent to occur. Subjective approach, again, what most people use, they base it on judgment, personal evaluation, and then the relative frequency approach. This is the approach, by the way, that we use in statistics in general. When we collect data, we're going to use the relative frequency approach. Okay, so that's that particular section. So now we'll go to 6.3. And let's see, 6.3 would be, I guess, the basic properties. I think that's the one. see this. Yeah, that's it. Basic properties of probability. All right. So what are the basic properties of probability? Well, they're sort of listed right on this page right here. So here we're using again the symbols for an event being some capital letter. In this case, we're using the letter E. Notice that the letter S is never used because it's reserved for the sample space. So we try to avoid using the letter S when we describe an event because S typically is the sample space. So for the first one says, for any event E, the probability, remember P with parentheses, with the event inside, means the probability of that event. The probability of any event is less than or equal to 1 or greater than or equal to 0. It cannot be outside of this range. Number 2, if S is the sample space for a chance experiment, the probability of the sample space itself has to be 1. It absolutely has to make sense, doesn't it? Because if you look at the classical approach, the denominator is the number of outcomes in the sample space. And if we want to know the probability of the sample space, well, the numerator would be all the outcomes in the sample space. Well, obviously, the numerator and denominator would be the same number, and we know that when we divide the same number by itself, we always get 1. So the probability of the sample space is 100%, absolutely certain. If two events are mutually exclusive, the probability of E or F is simply the probability of E plus the probability of F. Notice that it has to be mutually exclusive. There is another formula if they are not mutually exclusive, and we will talk about that next time. But if two events are mutually exclusive, then the probability of E or F, or the probability of E union F, is simply the sum of their individual probabilities. Basic property number 4 says for any event E, the probability of that event plus the probability of its complement, not E, has to be 1. And it makes sense because E, the event E is a subset of the outcomes of a sample space, and not E would be all the other outcomes of that sample space. So if we add them together, we get the entire sample space. So the probability of an event plus its complement must always equal to 1, because this left side here is the same thing as the probability of S. Now, because of that, a very handy algebraic equivalent to number 4, this one here, is if we subtract one of these from both sides of the equation, we get these two equations here. So if we know the probability of an event, and we want to know the probability of its complement, we simply subtract the probability of that event from 1. Because again, if we subtract the second term here from both sides, we get that first equation. Excuse me, I'm sorry. If we subtract the probability of E from both sides, we get that first equation. Similarly, if we subtracted the other probability of not E from both sides, if we subtracted this from both sides of this equation, we would get the second one here. I hope you can see that both these equations, these two equations and the number 4 here, this equation, are all the same equation. Just a little bit of algebra showing. And why do we want to know these? Just because it sometimes makes it a little quicker to calculate the probability that you're being asked to solve. Sometimes it's just a little quicker. All right, so it's a useful thing to know. Take a look at this one here. This one's a little complicated, but I'll show it to you anyway. All right, so this is a paper talking about preventable deaths due to problems in care in English acute hospitals. All right. So basically, they're saying that 5.2% of the deaths that occur in English hospitals were preventable. All right. So 5.2% of the deaths were preventable. Now, why why are they preventable? Because of 4 possible reasons that they happened. Either the patients weren't monitored well, there were some errors in diagnosis, inadequate drugs were given or fluids were given, or some other reasons, some other errors. All right, and based on the statistics that they gathered, they came up with these percentages of the preventable deaths in those 4 types of errors. The 31% of the preventable deaths were due to poor patient monitoring, 30% diagnostic errors, 21% due to drugs being given incorrectly or fluids, 18% for other reasons. Yet these percentages would come up to 100%, right? So suppose you came up with these 4 events here. Number 1, a 0, 1. Notice they all use the letter 0, but they use 1, 2, 3, 4. So 01 is the event that the death was due to poor patient monitoring. The 02 was due to diagnostic error. 03 is due to the inadequate drug or fluid management, and 04 is for any other errors. All right, so those are for those 4 types of errors. You could actually, and this is one thing that we will be showing you, or I'll be showing you in this course, we could actually show this in a table where we have along the top row here a list of all the outcomes, and then below it the probability of each one of those outcomes. Right, so this is, I kind of like tables like this. Visually, it seems more appealing than simply listing them in some other way. All right, so suppose you have this here. This is actually, you'll learn not Monday, but the following Wednesday, when we start talking from chapter 7, you'll learn what's called a probability distribution. This is a probability distribution. Suppose you have another event, the event that a randomly selected preventable death is due to poor patient monitoring, a diagnostic error, or inadequate drug or fluid control. In other words, it's due to one of these 3 errors. Now, these are mutually exclusive errors, right? They have nothing in common, these particular events, okay? We want to know what's the probability of event E that it's due to one of these 3. Well, one thing you could do is simply add up their probability since they're mutually exclusive. So you get 0.61, 0.82, right? Another possibility, if you were clever, is to use one of those special formulas and say that the probability of this of the complement of event E is 1 minus or is 0.18, right? Is this one here, the other errors. So the probability of event E is 1 minus the probability of not E, the complement of E. So it would be 1 minus 0.18, which also would be 0.82. So you can either add these 3 up, or you can say 1 minus 0.18, which is not included, and you would get the same answer. All right. Here they're showing the situation, or the case 1 where you were adding the 3 probabilities together, and then they said, well, why don't we use that formula, and we get the same answer. All right. So there's 2 different ways of answering that same question. And you might say, I don't know if I'll remember this formula. You don't need to remember it. Just know it's quicker, but it's not necessary. If you want to add up all the others, you can do that. Equally likely outcomes. This is the case where we have chance experiments like flipping a coin or rolling a die, or handing out 5 cards in a poker game. Don't worry about these formulas here. They're saying, what is the probability of each of the simple events that are equally likely? It's just 1 divided by the number of events, right? So again, you roll a die. There are 6 possible events. 1 dot through 6 dots. What's the probability of rolling a 2? 2 dots. And you roll a die. Well, it's 1 divided by 6, because there's 6 possible outcomes. That's an example of what they're talking about. All right, so if you have a certain number of equally likely outcomes. You just count the number of events for that event and divide by the number of outcomes. In a similar way, we have the addition rule for mutually exclusive events. Once again, if two events, E and F, are mutually exclusive, we say E, what's the probability of E or F, or E union F? It's simply the sum of their probabilities. And this is a case of two of them. If we have K meaning some number of these events, so K could be 10, for example. So if we had 10 events, and they're all mutually exclusive from one another, then we simply add up their individual probabilities to get your answer. And we say E1 or E2 or E3 all the way up to E10. All right, so the probability that any of these K mutually exclusive events occurs is the sum of their individual probabilities. Okay, so they're just giving you an example here. See what it looks like. Yeah. So suppose you have three on a large auto center. Suppose you have 3 Japanese type cars: Hondas, Nissans, and Toyotas. Okay. So we will denote each one of those with the event E. So if a car is a Honda, we call it E1. Car is a Nissan, E2. Car is a Toyota, E3. And suppose these are the probabilities of each of, if you selected a car at random, what would be the probability of selecting a Honda, which is 0.25, selecting a Nissan, 0.18, selecting a Toyota, 0.14. Notice that these numbers don't add up to 1, which means there are other cars on the car lot besides these 3 cars, okay? And we want to know what's the probability of that a car is selected at random, that it's either a Honda or a Nissan or Toyota. I hope you realize that those are 3 mutually exclusive events. A car cannot be both a Honda and a Nissan, or a Nissan or a Toyota. So when you add up, you simply add up their probabilities if you see the word or. What's the probability of one of these occurring? It's simply the sum of their probabilities. Now, what's the probability that the next car that's purchased is not made by one of these 3 manufacturers? Well, that's the complement of this probability that we just calculated, isn't it? If this is the probability of getting one of these 3 cars, what's the probability of not getting one of those 3 cars? If we select the one at random, it would be 1 minus 0.57. This is where that formula is useful. So if I want to know what's the probability that if I selected a car, it's not one of these 3, it's 1 minus 0.57, which is 0.43. This is a fancy way of writing it. You could write not next to one of these 3, or you can put a C for complement outside of the parentheses around the union of these 3 events. You need to know all this notation? No, because I would just ask you for the answer. All right. And that is the 3rd one here. So we're going to go to our 4th one for today. Okay, and that is this one, conditional probability. Now, what we have learned so far, the probabilities do not depend on any other events. If I ask the probability of an event, there's no information about another event. For example, if I ask you right now, your personal probability that it's going to rain tonight at 2 o'clock in the morning, or tomorrow morning at 2 o'clock in the morning, you would give me, you know, without looking at a weather report, you would give me some sort of assessment, maybe based on the idea that it's raining now, you might say 70%. But then you look it up on your phone and you see, oh, wait a minute, it's not supposed to rain tonight. So you change your probability to 10% instead of 70%. That's called conditional probability. You're changing the probability of one event based on the knowledge of another event. All right. And that's what they're saying up here. All right. Now, let's say we have a population in which 0.1% of all individuals have a certain disease. Now, what's 1.1%? That's 1 out of 1,000 people. All right, so it's a rare condition. All right, now, it's difficult to tell, apparently, for this particular disease, based on a physical exam, whether you have it or not. So there is a diagnostic test. All right, there's a test. Just like if God forbid, you had COVID, or you had symptoms of COVID, you wouldn't know unless you had the COVID test, right? For sure. So same thing here. Let's talk about another type of disease. Right, but it says here, unfortunately, the test is not always accurate, just like the COVID test is not always accurate. Of those with positive test results, that means the ones that say you have the disease, it says 80% actually have the disease. So what it's saying here is that if you take the test and it's positive, then in actuality, 80% actually have that disease. All right. So with the knowledge that a person had a positive test result, there's an 80% probability that you have the disease. Now remember, without that knowledge, we can only say 0.1% probability of having the disease. But with the knowledge that you have a positive test result in a lab, the probability shoots up to 80% chance that you have the disease. Now, there's a 20% chance that you don't. That's called a false positive. But regardless, the probability of you having the disease has changed with the knowledge that that you have a positive test result. You've gone to a doctor, they've ordered this test, you've taken the test, and it shows that you got a positive test result, right? So there's an 80% chance now that you actually have the disease. So here's some notation here. We're going to use capital E to represent that the event that the individual has the disease, and F is the event that the individual's test is positive. That means it shows that you apparently have the disease. If we write this here, the probability of E with a vertical bar F, what we're saying is the following. What is the probability of having the disease? And the bar here means, given that, F, that you took the test and it shows positive. It's giving you a positive result. So in the example that we just gave, the probability E given F is 0.8, because if you remember, there's an 80% chance that you have the disease if you have positive test results. Right? So this probability is 0.8. If I just ask you what's the probability of E, which is the probability of getting the disease without any information about a test result, the answer is 0.001. If you convert this to a decimal, which means divide by 100, you get 0.001. Okay. So this is called a conditional probability. It's a probability of one event conditioned on knowledge about another event. Okay, and again, I just went over this with this example that we just gave. So probability of the event E is very unlikely without any information, but with the information that you got a positive test result, it becomes likely, right? 0.8 is pretty high probability. Now, don't be frightened by this formula because it's not meant to be frightening. But this is an equation which gives you a formal way of calculating a conditional probability given information about the events E and F. It says that the probability of E given F, given knowledge of F, is equal to this ratio. The numerator is the probability of E and F, the intersection of these two events. And the denominator is the probability of F. It's the probability of that event that we know. All right? That's the probability in the denominator. And this is a formal definition or equation for a conditional probability. It assumes that the denominator is greater than 0. Obviously, if it's 0, we can't divide a fraction by 0. But we do make that assumption that the probability of F is some non-zero probability. Now, many times in statistics, we're going to be given a table that gives us a great deal of information about certain events. For example, here, suppose we wanted to study, suppose many people were studied, and these were people who were hospitalized, right, with a cardiac arrest, a heart attack, basically, all right? And they were given this procedure called defibrillation, or defibrillation, which means an electric shock. You've probably seen this. People get given this, maybe in a movie or something. And it's supposed to be given within 2 minutes of the heart attack, but sometimes obviously you can't. So the question sometimes is asked, what is the survival rate of those people if they were given this procedure within 2 minutes versus given the procedure after 2 minutes? So basically what happened is many people were in this study, and they looked at the medical records actually of 6,716 people in the study who suffered heart attacks and were given this procedure. And what was recorded was the time from the time of the heart attack to the time of the procedure. It's either 2 minutes or less or more than 2 minutes. Notice that in the right corner here is the total number of people in the study, 6,716. Running along the first column here is the size of the hospital that did the procedure. All right, so hospitals were broken up into 3 types of hospitals based on the size of the hospital: small, medium, or large hospitals. So, and then within each of these hospitals, we counted the number of people who received the procedure within 2 minutes, and those who received the procedure after 2 minutes. Now, how do you read this table? Well, the number of people in the study who were treated in small hospitals was 1,700 people. You could see it, right? Just move your cursor all the way to the right. The total number of people studied in the small hospitals was 1,700. In the medium-sized hospitals, 3,064. And in the large hospitals, 1,952. You add these 3 numbers up, you get your grand total 6,716. Notice also with the columns here, with the 2 minutes or less, or the more than 2 minutes, there were 4,689 of these 6,716 patients who received the treatment within 2 minutes, and there was 2,027 of them that received the treatment after 2 minutes. And if you add these 2 numbers up, you get 6,716. So if you could see how this table works. Now, what if I wanted to know the number of people who received the treatment within 2 minutes and were in small hospitals, in a small hospital? And the answer to that would be 1,124. How did I find that? 2 minutes or less, that's the column, and the row is small. So I find the intersection of those 2 minutes or less in small hospitals, and I get 1,124. If I wanted to know how many people received the treatment in a time that's greater than 2 minutes, and they were in large hospitals, that would be 565. More than 2 minutes, intersecting with large hospitals, that row and column intersects at 565. All right. Is everybody clear on that? All right. So let's go to the next page here. Here are the events. S represents the event that the selected patients at a small hospital. Now they did use S in this case here. Could mean sample space, but they used it. M is for medium-sized hospitals, L is for large hospitals. And what does D represent? That the person received this procedure in 2 minutes or less. Now, why didn't they have one for greater than 2 minutes? Because the complement of D is greater than 2 minutes. All right, so you didn't need a separate event for greater than 2 minutes. D complement is greater than 2 minutes. So if you wanted to know, for example, what's the probability that a person received the procedure in less than 2 minutes, it would simply be the number of people who received the procedure in less than 2 minutes, 4,689, divided by the total number of people in the study, 0.698. And another way of saying this is 69 98.8% of the patients received timely defibrillation. All right. Now, suppose we wanted to know the following question. How likely is it that this patient, let's say, it is known that the selected patient was at a small hospital. All right. So this is knowledge that we now know. The patient was at a small hospital. How likely is it that this particular patient received defibrillation in 2 minutes or less? Well, if we know that the patient was in a small hospital, right, which means this row here, there were 1,700 people in the small hospital, we don't need to think about the other hospitals, do we? We simply now can look at the 1,700 people that were in small hospitals, and we want to know what's the probability that they received timely defibrillation, which is the 1,124 of them. So 1,124 divided by 1,700 would be the answer to that question. Now you say, well, why not divide by 6716? Because we now know that the person was in a small hospital. So it can't be out of 6,716 because there were only 1,700 people in the small hospital. We can eliminate the medium and large hospitals when we answer this question. So this is what's called a conditional probability. It's the probability of D, probability of getting that treatment within 2 minutes, given that S. What's S again? Small hospitals, given that we know it's small hospitals. Now, we could use this formula here, but we would get the same answer, okay? In other words, we could find this probability, and divide them. Or we could simply do 1,124 divided by 1,700, and we get the same answer. Okay. These are other possibilities too that you could read through the same type of case. It's also possible, what if we knew that the person received treatment within the 2 minutes? What if we knew that, and we want to know what's the probability that that treatment was given in a large hospital? Back to the chart. Well, if we know that they received treatment in 2 minutes or less, we know that's for 4,689 people. What's the probability that that person received that timely treatment within a large hospital? It'd be 1,387 divided by 4,689. We don't use 6716 here because we know that they received treatment within 2 minutes. Again, you'll get examples of all this when I give you homework on this, and I'll talk more about this next Monday. Okay, I think we're running out of time here, so I'm going to stop here and continue with this next time. Well, that was it anyway. So I think we're done with this. I'll give you more examples of this next time, and we'll finish chapter 6 next time, which is next Monday. So what's the story now? The story is that you should complete homework 2 by tonight, 11:59, and also study for your first test, which is going to now be on Wednesday. All right. So any questions about anything that we've covered today, or any procedures or anything else? Everybody's good with that? Best review tips for the test? Best review tips for the test is make sure you read everything and go over the videos. Now, it takes a lot of time to do that. The people who spend the time going over, reading the textbook and listening to the videos will do well. And make sure also that those videos that deal with finding the histograms, finding box plots, you should know how to create, know how to interpret a box plot, a histogram, and other types of graphs that we talked about, and also how to enter, this is very important, how to enter a data set into a list in your calculator, and how to go to one variable statistics and look up the mean, the median, right? The standard deviation, the lower quartile, upper quartile, maximum and minimum values. All of that can be looked up in one variable statistics. Make sure you know how to do that. Working with your calculator will save you a lot of time. All right, anything else? 22 multiple choice questions, 5 points each for a possible score of 110. All right, that's it. All right, so I'll stop the recording, and I know I ran over for about 4 or 5 minutes, but hopefully that was worth your time. And I'll see you guys on Wednesday. The test will start at 12:35. All right, 12:35. Good.
Thank you. Have a good one.
You too. All right, take care.
Thank you.
You're welcome, and I'll see you on Wednesday.
Thanks.